Hello and welcome to another creative coding video. This is the third in a series on ray tracing. Now, just as a reminder, ray tracing is about using mathematical methods to model a scene with objects and to try to make it look fairly realistic by modeling how light moves in the scene, bouncing off objects, reflecting, thinking about how shadows work, thinking perhaps about refraction as light moves through glass, for example. And as you'll have seen in the first video, you can create some really sophisticated, really impressive looking images with this technique. In this series, we're just looking at the very basic techniques, just so we can build a good foundation, and then if we want to, we can take that in new directions and with very new modern ideas about how to do ray tracing. So in the very first video we introduced how we might mathematically model objects like a light ray and follow it through a scene. We also looked at how we might mathematically model a sphere. The important thing we did in that video, in the first video, was to test for intersection, for testing whether a ray hits an object or not. And that was quite a bit of work, but it was important work because all of ray tracing is built around that very concept of light hitting an object or not hitting an object. In the second video, we then thought about shading an object and thinking about, well, which parts of the object will be darker and lighter than others. And we did that based on this idea of illumination, to what extent a surface is pointing towards a light source or not, and making it lighter if it is. We also included an extra factor which took into account the direction in which light rays are reflected away from a surface, and that was a nice refinement. We said we might look at reflection, but actually, having thought about it, we'll do that next time in the final video, the next one, because there's a few other things that we wanted to kind of get in place first, and if we did it all in one video it would be quite long. So today's video builds a little bit more on the basics and gets us ready for the final video where we explore reflection, which is, I think, the most impressive kind of thing that we can model. So today we're going to be looking at how we can code for several objects in a scene. That's a very easy thing to say, but how we code for that does require a little bit of thought. Before we do carry on, I just wanted to make a couple of refinements just to kind of explore a slight side kind of direction. The very first one was the colouring of the sphere that we created before. I wasn't too happy with it because it looks a bit too light last time, so I'm logged into Open Processing as usual. I've created a new sketch and the code is the code we created last time, and this is the line that defines how we colour points on the sphere. And you remember the lighting factor was dependent on whether that surface was pointing towards the light or not, and whether the reflected ray was coming towards us or not. Now this, having thought about it, the values in this red, green and blue combination are quite high already, so I'm going to lower them so that they change like this. Now remember, lighting goes from 0 to 127, that was our factor here, because these are cosine factors which will also clip to go from 0 to 1. So this will go from 0 to 127, which is half the RGB range. So our red can go now from 127 up to 255 roughly, and the green and blue will stay at a lower 0 to 127. I think that should create a nicer effect, so let's see. There you go. That's much better, I think. It's red, which is what we wanted, and the darker areas are darker while still having the light areas fairly light. So I think that's a nice kind of improvement, I think. The other one looks very pink. Great. And the other thing I wanted to explore was see if you can simulate a matte surface rather than a shiny surface. Now, one of the ways of doing that is to think about what a matte surface actually is. So the reason a surface is matte, if we looked at it with a microscope, is that it's often rough, either at a large scale or at a microscopic scale, which means that light, when it reflects off it, reflects in different directions. So here we're looking at a surface which is not smooth. It's not shiny like polished glass or polished metal. This thing is jiggedy jaggedy, which means that when light hits it, it bounces off in all different directions. So one way of thinking about this is, one way of simulating a matte surface, a non-shiny surface, is to add some randomness to the reflected ray, and that can contribute to the kind of the lighting factor. Another way to think about it is to say that the normals, it's one of the normals that are the vector that sticks straight out from a surface, that those are now randomized, and that can also have that will also then affect the illumination factor as well. So let's try both, just to kind of compare the two approaches. So in our code, going back to it, we calculated reflected ray, from which we then calculated a factor which influenced the lighting, a sort of a cosine factor. If you need a reminder, I do recommend going back. So let's add some code to randomize the reflected and we can say reflected ray equals, and we're going to add to that a random vector. So p5.vector.add, we're going to add to the reflected ray some random vector. So random, we don't know what that is yet, we don't have to code for it yet. Once we've done that, we want to normalize the reflected ray again. Normalize. Now, having looked up the reference for P5JS, there is actually a function, a convenience function that does this for us, and it's called P5 vector with a capital V random 3D with a 3 and a capital D. So this bit of code here will create a random vector with 3 random values between sort of 0 and 1. Oh, is it 0 and -1? Is it -1 to 1, or let's look it up. It's good to kind of remind ourselves what it does. Let's see. So the reference says it creates a new random 3D vector, and yep, it can take negative values as well, which is good, which means it's pointing in all directions. So this is now adding some noise, randomness, to the reflected ray. Let's see the effect that has. Oh great, okay, so that's much more speckly, and from a distance it does look less shiny and smooth compared to the other one, so it's closer to being a matte surface. Now in this tab I've got the previous image open so we can compare. Now that's shiny and smooth, and that's less so. So you can see there is definitely a difference there. Now let's try the other approach, which said that we would not randomize the reflected ray, but actually we would just randomize the normal. And the normal is given to us by the sphere object, part of the intersection method. It returns a boolean which says hit or not, and it gives us an intersection point and a normal. Now what we could do here is randomize this normal. So we can say, well, not randomize it, but add some randomness to it. Normal equals p5.vector.add normal p5.vector.random 3D. And we're normalizing it in the next line anyway. So let's see what effect that has. Great, so that's again having a similar effect. It's much more subtle this time. It's not so stark. And I think comparing it again to the smoother image, it is a much more subtle effect, isn't it? But yeah, so that's another approach. So I just wanted to cover that, just to kind of give you an idea of several ways of simulating different kinds of surfaces. In the next video, where we do simulate reflections, we'll also cover other kinds of texture where there are patterns on the surface, so we'll have a look at that as well. Great, so what I'm going to do for the rest of today's tutorial is focus really on the meteor challenge of having several objects in a scene and giving them separate colours as well. So let's make a start. Let's bite off an easy part of the problem, which is giving spheres different colours. Now if each sphere is going to have a different colour, it makes sense to include it as part of the object. At the moment we were choosing a colour just independent of any object, we were just doing it directly in code. What we'd prefer to do is to have the sphere tell us what colour it is when we ask it, did this ray intersect you or not? So let's work backwards from that. So this sphere has an intersection function and it returns a yes/no for intersection with a ray or not. It contains an intersection point, a normal, and now let's return a colour and it'll be part of the object. So this dot RGB. Great. And we'll have to then define it as part of the object's data, and that can go here, which is then set when we create an object, we initialize an object. So this .rgb equals create, and we can create it as a vector, even though it's not really a vector. It's a nice way of just packaging up three numbers. Actually no, we don't need to do that. It can be a list, can't it? Yeah. Yep, we don't need to just say that. We can just say it's passed as a colour, which could be a vector, and then we just store it as part of the object. It doesn't have to be any more complicated than that. I'm avoiding using the word colour because that's a reserved word in it's an instruction in the language, so that would confuse things. So I'm just using col. Great, so that means we can create a sphere and define where it is, its radius and its colour. And all this appears to be doing is passing back to us, which doesn't seem like a great benefit, but it will be when we create several spheres. So let's think about how we might create a scene with more than one object. Having more than one object, if you've been following the tutorials, usually means creating a list and putting our objects in there. So that's what we're going to do. We're going to say, we can say scene list, scene, or list of scene objects, list of scene objects, or list of objects, and it's empty at the moment, and we can then add to it, we can say list of objects dot push onto it a new sphere. So we're just editing our previous code, And remember, we need to put in a colour now, and we can create that as a vector. Even though it's colours, red, green, blue, we can use this vector thing because it contains 3 values, so it's a kind of convenient way of packaging that up. And it can come in useful if we are adding RGB values together, which you might end up doing. So that's a good reason to package up RGB into a vector. So let's create a red one. Red. So our red is 25500. So that creates one object. Let's create a second one, and all we do is just push a new object, a new sphere, onto the end of that list of objects. But we do need to create it at a different location and size, and hopefully a different colour. So let's maybe move this one to the left a bit. -2, -1, and then this one can be, so this one is to the left and this one's to the right. That one is down a bit, and this one can be up a bit, and that one can be, this one can be closer in the Z direction. Let's give them different sizes. Make them just a bit smaller, maybe 5 and 4. Okay, let's not have them both red. Let's have this one as green. So we now have a list of objects. We now need to think about how we test for intersection, because previously we worked through all the pixels of the viewport and we just had one sphere that we were testing with. Let's draw a sort of pen and paper sketch to kind of think about how we might do this. It's always good to have a sort of pen and paper sketch. It really kind of helps with kind of clarifying our thinking. Okay, so if we have our camera here, or our eye, we've got our viewport and we're sending rays into the scene, it could be that we don't hit any object. It could be that we hit one object, which is just like before, but it's also possible that we can hit more than one object, like this. That's the case we need to handle, because that's likely to happen. So what would we do? Well, let's think in plain English and not in terms of code. In plain English, I'm following a light ray into the scene and I hit this object, which at this pixel here in that viewport, that rectangular viewport, which colour should I be colouring that pixel? Should it be the colour of this sphere or this sphere? So sphere 2 and sphere 1. Well, it should be this one because it's in front of the other one. Now I can carry on with this light ray and test that object, and we should test all objects. That's going to sound too obvious to say, but we need to work out a way of saying, well, it's not this colour, it's this colour. And what sticks out at us when we draw this kind of sketch is, well, it's the nearest one, which means we need some way of working out which one is nearer to us. And we've kind of done that before. We worked out using that kind of t value. Remember the ray equals the camera position plus t times the direction, and ct and r are vectors. So we can work out the length of that ray when it intersects. So we can do that. And I'm wondering if it's a naive thing to do to just use the z value. So imagine this scene where x is coming there, y is there, and z is in this direction. So x, y, and Z is into the scene. Now should we just use the Z? More strictly speaking, it should be the magnitude of that vector. Just wondering if we can save a little bit of calculation just by looking at Z. Let's think about that as we code. Okay, so this means we need to work through all the objects in the list, test all of them, and keep a track of which one was nearest and the colour of that nearest object. Let's do that. So looking at our code, we work out the current position, work out the ray direction, and this is the bit we need to change now. So we'll keep the old code there for now, because we can refer to it. We need now to think about test all objects in scene. And we can loop through those by saying for var object of list of objects. And we've done this kind of loop before, where we're not counting, keeping a loop counter like we've done here. What we're doing is we've got a list of objects, and every time we work through that loop, this variable is each of the objects in the list. Quite a handy kind of construction. Great, so thinking aloud, we're working through that list of objects, and we want to test intersection, which we've kind of done before, so we could copy that code. So let me copy that and reuse it here. We'll need to kind of update it a little bit. And remember, we now have an additional thing that the sphere, or the object now, it's object, we don't have a sphere, that it returns us, and that's the color. So we can say RGB. Great, so this is now testing each object, and you might test the first object and find that it doesn't hit. You might test the second object and find that it does hit, but then you might find that the third object doesn't hit either. So we need to not use the last value of hit. We need to check if there was a hit and then keep a separate variable if it was the nearest one so far. So to do that, we need to keep some variables outside that loop, referring to the nearest point so far. So nearest point. If that doesn't make sense, let's kind of talk about it here. So as we have a loop here, working through each object in the list, and what we want to do is we want to maintain information or knowledge about which was the nearest one. So outside the loop we say nearest was, well, we don't have to set it to anything at the moment. And then as we work through the list, we find one and say, okay, that's the nearest so far. We hit another one, another object. Maybe that's not nearer, so we keep the variable that tells us which one is the nearest unchanged. Then we look at another object and find, oh, maybe that was nearer. So we need to update this variable, this information that tells us what the nearest one was. We might hit another object and find, nope, that did hit, but it was further away, so we don't update this. And then we might find another object which actually was even nearer, so we update that one. And then at the end of the loop, that information about the nearest one will be correct. That's what we're trying to do. So we need to know, so var distance to nearest, so we'll need to keep that distance to nearest point. So before we enter that loop and test all the objects, the nearest point is going to be far away, and actually we're lucky that JavaScript does have an infinity value. So this one, you can look it up. What it does is it allows us to do a comparison, like less than, and it's always more than a number, which is great. So that's what we're starting with. So before we've entered the loop, the distance to nearest point is infinity, and that will get updated as we go through the loop. It's quite handy, isn't it? We'll also have the nearest intersection point. We don't need to fill any value there. Var nearest normal. These are the things that the intersection function returns. So we keep track of that. And the reason we're creating them before the loop and not inside the loop is because we want to be able to refer to them once that loop is finished. So the scope needs to be outside that loop. What else do we need to keep? Oh yeah, the colour, that was important, wasn't it? Var nearest, let's call it nearest RGB. Do we need to keep track of anything else? What if none of the objects intersected a given ray? We need to know that outside that loop so that we know whether to colour the point or assume it went into the sky. So we can say var, not hit because we're using that already, let's call it intersected. And to start with, it will be false, and if it ever hits an object, we'll set that to true, so that when we come out of the loop, we know if there has been any intersection at all with any object. And if there has, we'll know it's the nearest colour to use, and we can use the nearest normal and the nearest intersection point to work out the shading. Great. So in here then, we need to update those variables, so we can say if there was a hit, we can say intersected equals true, and we never have any code to say it's false because it starts off as false. And if an object didn't hit, another one might, so we only ever need to kind of change it to true if it hit. The nearest point, so we can say nearest point. So we say, is it the nearest point? So how do we calculate that? Well, it's the intersection point, isn't it? So it's the nearest, the distance is from the camera to the intersection point. So the vector we're calculating, let's look at that picture again. So this is the camera, this is the intersection point, which could be here. It's this vector, I minus c, intersection point minus c. It's the size of that, the magnitude of that, that's the distance. Haha, so we didn't need to kind of worry about just using the Z, we can do this. Great, so it's p5.vector.sub camera location, and taking away from that is the intersection point. Actually, no, it's the other way around, isn't it? It's the intersection point minus the camera location, and then we need to work at the magnitude of that. p5.vector.mag for magnitude does that. That is the distance. So var distance to point is that. Now, is that the nearest so far? So if distance to that point is less than the distance to nearest point, then update distance to nearest point equals that distance. Do you see what we're doing here? We're saying we're working at the distance to the point, the intersection point. Then we're saying, is it less than the currently recorded distance to the nearest point, which starts off at infinity? If it's less than that, then now update this distance to the nearest point to be that distance. And if it's not, we don't do that. So you can see that over time, as we work through the list, this distance to nearest point will get updated any time an object is nearer than any previously nearest object. Great. Okay. Yeah, we need to also update the colours as well, don't we? Yeah, so it's not just the fact that we've worked out that it's the nearest object so far. If it is the case, we're saying nearest intersection point equals intersection point of the current object. We're also picking up the normal, so nearest normal equals normal, the one that we got from the current object, and nearest RGB equals RGB. So if we found that the current object is nearer than any other one, we update all those variables about the nearest distance, the nearest point, what the intersection point was, the normal and the colour. So in a sense, these variables track the nearest object as we work through the list, which is what we want. Great. So once we've done that, at the end of all that loop, which goes where here, that's the testing list of objects loop. Now, once we've done that, we now have information about the object which was nearest, and we can now work out the colour. So colour, if intersected, yeah, if it was if this is true, not the hit but the intersected variable, which is only true if at least one object hit the ray. So if intersected, then we can work out, as before, the various kind of factors taking into account whether the surface is pointing to the light source or not. So we just need to update the code. So instead of light location, we have light location stays the same. So we have nearest intersection point. That's fine. Next line, we use the nearest normal. Nearest normal. Nearest normal there. Do we need to change anything else? think the only thing we now need to change is the RGB. Great, so let's think about how we colour. So we are picking up the RGB of the nearest point. Let's write it out. So it's going to be a P5 vector. So the red bit will be nearest RGB.x, even though it's not really x, it's the first value which was red. And we want to do something with those to do with the lighting factor. What's the easiest way to do that? Well, we could actually just multiply the lighting factor, the RGB, so actually we could say scaled. We're scaling the RGB up by the lighting factor. Scaled RGB, scale RGB by lighting factor. So we say, do you want to create a new variable? Yeah, why not? var RGB scaled equals, and what we want to do is nearest RGB and somehow multiply by lighting, and we know that we need to use the P5 vector functions to do that. P5 vector nearest RGB times the lighting, which is a scalar, it's not a vector, so that means it's mult. Dot mult. So that will multiply those two. Do we now need to scale those back up to 255 or not? So this will be, yeah, this will be quite large, won't it? This will be up to 127. Let's not do that. So this will be from 0 to 1. That will be RGB nearest to 1. Yeah, I think that could work. Don't think we need to do anything else there. In fact, we don't need to create a new variable. We can just say the nearest RGB is updated by multiplying it by the lighting factor. So we can say update RGB with lighting factor. That should work. I don't think we need to do anything else there. Let's see if that works. And as usual, I think we might have a typo, but we'll find out. Let's go. Great. That actually worked. Wow, that's quite rare to be able to write a lot of code and then not have a kind of a typo in the code. So we've got two objects here, and the green one was nearer, so it's in front of the other one, which is good. It's a bit dark, so we can fiddle with the colours a little bit, but the important point is that we correctly had the green sphere painted, in terms of pixels, in front of the other one. So we don't see a bright red here, we actually see the darkness from the bottom of the green ball sphere, even though we know that there would have been quite a lot of red sort of highlights there. Let's move them around a little bit. Let's try that again. So maybe I can make them a bit bigger. So maybe I'll make that 7, that 5, and I'll move this one bit more to the left and this one a bit more to the right. Do we want to do anything about the colouring? Well, we could undo the Phong factor, so we can comment that out. That could spread the highlight a little bit. Let's see what effect that has. Well, it certainly spread the highlight. Now that looks a bit fishy there. I think it's because the two balls have merged a little bit. Maybe I'll bring one of them much more forward. I did make them larger, didn't I? Maybe I'll make them small again. 6 and 4. And maybe I'll do... yeah, that should be enough. Great, they're two objects are not sort of going into each other now. That's fine. I could spend a lot more time now fiddling around to try and make these objects lighter in some sense, but that would be a distraction because it's not really about the ideas of ray tracing. It's more about how we fiddle around with red, green and blue values, and I think we won't need to anyway, because in the next final video we will be looking at reflection, and there will be more chance of light bouncing around, being reflected, to colour some of the dark bits. So we'll leave that until then. If you want to have a go at your own ideas for adjusting that colour, you certainly have a go. So we'll end today there, slightly shorter, but it was important to go through first just having a look at different ideas for making the surface less shiny, and a really easy kind of approach is to think about a matte surface as actually being a little bit rough, so the light reflects off in slightly randomized directions, and that kind of worked fairly well-ish. But the important thing that we did today was to develop the kind of machinery, the method, the code for how to have a scene with several objects, and each of them having a different kind of colour. We might even have different textures, and they're independent, so each object has its own information, and it's quite extensible. So just before I do finish, what I'll do is I'll just add another sphere to the scene, and it's as simple as saying copying and pasting just that line of code, and I can have that central, and I can have it further high up. I suppose we can say it's at a height of say 8, make it smaller and have it as yellow, which I think is this red, green, blue value, and the code we've written will just work because it's going through that list of objects and testing them. Do I want to make this a little bit X, Y? I want to make it higher, don't I? So I'll make that say 4, and I want it closer, so I might do -2. What was yellow the other combination? 2, 5, 5, 0. I might move this even more to the left. I might move this all more to the right. There we go. Have another go at that. Brilliant. So that worked. So you can see how it's really easy now to just add more objects to the scene and have the ray tracing code kind of take it into account. We'll stop there. So that's been a good foundation and getting us ready for the final video next time, which I think is the most exciting one, which will look at reflections. So we'll be able to see reflection of each object in other objects. I think that'll be quite exciting. So fantastic. Have a go yourselves. Maybe you can write code to randomize the creation of these things. That's a fun thing to do. So you might say we've got a loop that creates 10 of these at different sizes and different colors. That's a kind of fun thing to try. See you next time. Bye.